Good evening, sir. What are we going to do in the session today?
Yeah, hello everyone. In this session, we'll be discussing the week 10 concepts.
Week 10.
Yeah.
Okay. So I think week 9 concepts are not being discussed.
Is it so?
Like those are not being discussed by those are not discussed in the instructor sessions, but yeah, those are discussed in the um, TA sessions.
So for week 9, the session was not happened or it's happened, they discussed the practice assignment or some other concepts.
I think for the week 9, it didn't happen. Like after our exam, I think today is the uh, session for the instructor one.
Okay. Mm. Okay, then we'll cover the week 9 concept briefly before going to week 10.
Okay.
Okay, the live stream also been started. Okay. So, how many of you know how to create a matrix? I mean, the pseudocode. Okay, only one. Week 9 deadline is over, right? Or is it still open? I think only week 10 deadline is coming Wednesday.
Week 9 deadline is over.
Okay, then we'll start this session. So, we'll briefly go through what is mean by matrices and how can we create matrices and where it will be helpful. And week 10 will see using matrices and what are the concepts that we will be studying? Because the week 9, week 10, week 11, week 11, sorry, week 12, all this weeks you will be studying matrices. And so you need, this is very important for end term as well. Okay. Sorry for the interruption. Is my screen visible now? Hello.
Yes.
Yes, sir.
Is my voice is also clear, right?
Yes, sir.
Sure. Okay. So far we have seen list and dictionaries, right? And so in quiz 2 exams also you might have seen the list and dictionary concepts. So so in list you cannot have random access, but in dictionary you can have random access using the key value. And on all the keys should be unique in your dictionary, right? And we have also seen the values could be anything. Values could be list, again it could be dictionary. So we have seen multiple levels of nested dictionary, and in list also the list of list we have seen. Okay. So but now here we are going to study about matrices. How can we create matrices, and why do we need matrices? Can anyone?
To find the relation,
Sorry,
to find the
to
relation between
find the
two
relation.
variables.
Any other advantage of using matrices? So the matrices are is will also be a dictionary, but it will be a two-level nested dictionary where you can access a particular node with basically the matrix is mostly used for the graph problems. So we generally store matrices in a graphs in a matrix format. Okay. Okay, let's look at how to create the matrices, and we'll look at some examples. Mm, okay.
Hello. Sir, Screen is not presenting, or you are not audible.
Sorry, I was facing some issues with my laptop. I think now it's better. Am I audible? Can someone confirm? Sorry for the interruption. Really. Again,
Yes,
second
you're
time.
audible, sir.
Okay. So, so we used to access the matrix using matrix of Ij, right? So generally, this we used to have m rows and n columns. I think in Max 1 also the matrices have been started. So the matrix will look like in this structure. So generally, this is how we represent the matrices, right? Where these are rows and these are columns, right? And but how do we create such kind of matrices using uh, pseudocode or any programming? So we here, anyways, in CT, we'll look at the pseudocode. And what is I and what is J. And basically the M rows means these are rows. In this case, the row is 3. You have row 1, row 2, row 3. And column 1, column, and you have 4 columns. This has column 1, column 2, column 3, column 4. It is a 3 by 4 matrices. So you can say 3 rows and 4 columns. But since dictionary support random access, so we can create a matrix using dictionary also, list also. But here we are seeing a dictionary of dictionary to create a random matrices. Okay. So let's look at how to create a matrices. So in order to create a matrices, we are defining the procedure create matrix. And what we are doing initially, we are just initializing it as an empty dictionary. And while I is less than 3, let's say for example, let's take 3 by 3 matrices, rows as 3 and columns as 3. So if I is less than 3, which is my rows, I'm creating another matrices inside my dictionary. The matrix of I, where I is nothing but 0. So the matrix of 0 will create another dictionary. And once you create another dictionary, you are again going to set a key value based on the columns. So this will set a inner key value. For example, the matrix of 0. Inside again there will be a 0. Since I initialize j is also equal to 0, it will be equal to 0. And next time you are just incrementing the j as plus 1. Then since you are inside the inner dictionary, I haven't gone to the this block of code since I'm executing this only. So matrix of 0, 1, which will also be 0, and matrix of 0, 2, which will also be 0. Once I completed this while loop, my I will be incremented. Now my I will be equal to 1. Then the matrix of 1, 1, 0 will be 0. Similarly, all up to matrix of 2, 2 will also be. So, and here the matrix of, 1, 2 will also be 0. This is how the matrix will look like. If I have to create a matrix structure in a dictionary form, so the matrix can be a dictionary with this 0 as one key, which is 0th row. So here we are uh, considering as a 0th row, but generally we used to first row, second row. 0th row is 0, 0, 0, 1. And in 0th row, again, we are having a dictionary. Here again, 0 as key, 1 as key, 2 as key. Again, here 0 as key, 1 as key, 2 as key. And 0, 1, 2 as a keys. And here we are just initializing as a 0 for all keys. So this is how the matrix structure can be represented through the dictionary. Any doubts so far? While creating the matrices?
No, sir.
Hello. Okay. So once this matrix has been created, so we'll see how to create a matrices or how to assign a value to the matrices. It's not moving. Okay. So now, how can we process something on that matrices? Okay, they haven't given anything here. Okay. Generally, what they do is, if you see carefully here, uh, they are sorting the keys of the matrices. So the matrix key is what? As we have seen here earlier, 0, 1, 2 as outer keys, 0, 1, and 2. And this is for the rows, right? The outer key corresponds to rows of your matrices, the number of rows. Actually, it denotes the number of rows. And if you take the keys of matrices of 0, actually it should be length. Yeah, they are just sorting it. Okay. This my matrix, if I say my matrix 0, and if I take a keys, and for the keys, if I take a length, this will give me the column number of the matrices. Any doubts here? Because this is a very, very important. Uh, First of all, you have to create a matrices, that's fine. But once you create a matrices, how can you access the matrices? Because first you need to iterate through the row, then you have to iterate through the columns, then only you can find the exact value of that particular uh, position in your matrix, right? So this sort nothing but it just sorts in ascending order. Key is already, uh, maybe let's go to the next slide and take a look at the example. Sure. Okay. In this question, what we are doing is we are trying to create a graph. As I said, matrices are used to create a graph. Okay. So what we are doing, n equal to length of keys of mark. Marks is your gonna be your dictionary, and which has the key values and it has all the details of subjects and the marks values. And we are creating the matrices and assigning the empty matrix, which is n by n. Basically, the number of records. It's based on the number of records in your marks dictionary. We are creating a n by n mental graph. That is nothing but we are creating a matrix dictionary and assigning to the mental graph. And for each I in keys of the mark, and for each j in keys of the marks. So what we are doing, basically we are iterating the keys of the marks dictionary. So where marks is a dictionary and it has some keys, we are iterating through it. And marks of I and j. So for example, the basically it should be a name of person or it could be something else. I don't know what structure it's been
Sequence number.
referred to.
Sequence number to marks.
Yeah. Yeah, someone has any doubt here?
So I said sequence number mapped to marks.
Okay, sequence. Okay, even if it is a sequence number, maybe it could be a roll number or sequence number, anything. So it can have some marks 70, 60, 55. Such kind of matrices can be there. So once you are iterating this 1, 2, 3, and again you are iterating through the 1, 2, 3. So what it this two for loop is trying? It's trying to compare each and every value within your marks dictionary. So basically, this one will be comparing with 2, and one will be also comparing with 3, and one will be comparing with other keys also. That is what this two for loop is doing. Similarly, once you go to 2, 2 will compare with this 3 key and go and so on, right? So this comparison is done in the mark dictionary. And ij mark distance. We are just taking the difference whenever we are comparing, we are taking the difference of that marks and storing it in the ij. If the difference is between 10 to 20, we are saying the mentor graph of ij could be well. See, we have initialized the mentor graph as a 0, 0 matrix. Right? So it will be, if I want to represent in a matrix form, everything is 0, everything is 0, and I found someone who can be a mentor. That means this is a student 1, and this is also corresponds to student 1. This corresponds to student 2, and this corresponds to student. So the student 1 can mentor student 2 if they are having a mark difference of just a mark difference between 10 to 20. Then he can mentor. That is what it is saying. Right? Any doubts here? Hello.
No, sir.
Okay. So next, again, it's kind of same kind of graph, but based on the subject. Now what we are doing, again, we are trying to create a mentor graph, and again, we are trying to create a mentor graph for maths and physics, and we are taking whether it has been paired or not. And for paired, again, we are keeping a separate dictionary to keep track of it. And what we are doing, we are iterating to the we are iterating to the rows of the mentor graph, and columns again the mentor graph. We are iterating. If math.mentor of ij, basically that means some student is mentoring, I student is mentoring j, then it is equal to 1 for math mentor dictionary. It is specifically for math. So that means here it is 0. That means I is mentoring j here, the student I. And similarly, the physics should also be a mentor. Uh, Similarly, this j student should mentor I in physics subject. So that is unconditioned, and is key in a paired dictionary. It should not be present already. So that means we are seeing this I and j for the first time in our paired dictionary. So if these conditions true, what we are doing, we are just taking paired of I and j. That means the paired dictionary will be look like it will have the student number as student 1, which has been paired with S2, and it can have also this key S2 can be paired with S. This is what it is doing. See, paired of I is equal to J and paired of J equal to 1. So it's storing in the reverse manner. See, both way it's storing. In this way, it's telling S1 is mentoring S2 and S2 is also mentoring S1. This is for the mathematics and this is for the physics. Okay. But in the description here, they have generally given one A can mentor B in one subject, B can mentor in other subject. But here we have in the code we have explicitly taken maths and physics. And the next dictionary is trying to find a popular, who is among popular. This is a lecture also, I guess. This was a lecture also. So now what we have is a mentor dictionary, popularity dictionary. And since we have already have the math mentor graph, so it's creating a mentor of that particular student. So math mentor graph will have the keys as a student roll numbers, right? So for that particular student, I'm creating a empty dictionary in the mentor graph or mentor dictionary. Basically, we are trying to store in a dictionary. So I might say as a graph in many of the times, but don't confuse it. Okay. For each I in rows for the math mentor graph. So what it's doing is again going with the rows of the math mentor graph and is checking whether the math mentor graph ij equal to 1 or not. If it is there, so it's saying the mentor of j of I is true. See, it's iterating to the columns, okay. And that means j is mentoring I. Student j is mentoring student. And we are setting it to true. And this also we are setting it to true if j is mentoring I for the physics. And we are setting it to true if j is mentoring I in chemistry. So basically what this does is if the j is mentoring I in any one of the subject, we are just setting it to okay. And finally, the popularity of j, we are setting it to be length of keys of mentor j. So for this particular student, what is the popularity? How many times I can set it true for this particular student j?
3.
How many times? It will be n times, right? Based on the number of wherever you see a student and in mentor graph it is equal to 1, that can be your the n keys. And if he is mentoring any one of the subject, then you are setting it to true. That means E can be this J can mentor I, student I, in any one of the subjects. Right?
Yes, any one of the 3 subjects.
And he can also mentor the other students. That is why we are iterating. So this popularity, what it will do, popularity of J, which is your mentor. So it will store the number of keys of the particular mentor, which is nothing but the number of students he is mentor. So it will be 5 or 6, 7 something for that particular student J. So this says the number of students that he is mentoring in any of the subjects. So this is what it's being calculated. So is it clear?
Yes, sir.
So for example, again, we are using the similar student. So similar student also follows the same kind of approach. Procedure create similarity graph. It's taking marks 1, marks 2, marks 3 as the dictionaries. And this marks 1, marks 2, marks 3 is nothing but it's a form of mathematics, chemistry or physics. It could be any of the subject where marks 1, marks 2, marks 3 are 3 different subjects. And we are taking n as the length of the keys of marks 1 and we are creating a similarity graph since considering this mark 1, mark 2, mark 3 all are having the same number of keys. So we are creating a similarity graph based on that n by n, the similarity graph. And we are iterating through the Marks 1 dictionary. And for J in keys, again, we are iterating to the same keys. But again, as I said, if we are having keys up to 10, this one will compare with 2, 3, and so on up to 10. This 2 will compare with 3, 4, 5, 6, 7, 8, 10. That is what this 2 for loop is doing. Okay. So basically, it compares, basically, each student compares with every other student. And ij difference 1, absolute of marks 1 of I, marks 1 of j. And ij difference 2, which is nothing but it could be max subject, it could be chemistry subject, it could be physics subject. So considering this is max physics, this is max chemistry and physics. So I'll take this difference also same. And after computing with every student, whenever we are comparing, so whenever we are comparing, if the difference in all three subjects is less than 10, that means I can say these students are studying very well or not very well. These kind of students are in similar category, I can say, right?
Yes.
If the student one has a marks of 90, 80, 70 in all three subjects, if student 3 has a mark of 85, 75 and 65, okay. So the difference between in all three subjects are less than 10. So I can say this student 1 and 3 are in similar category. I couldn't see much deviation from like less than 10 as a considerable similar students, right? If marks are less than student based on the marks.
టీమ్మేట్ ఆరా
Hello, is this clear? Please mute yourself. You guys were not. Is it clear?
Yes, sir.
Okay. Okay, then can we move to week 10? We don't have time to look at the PA or G or week 9. Uh, we'll complete the week 10 concepts, and
Yes, sir.
Monday there will be
Question.
one more session to cover week 10, because this is very important to in order to study week 11 and 12. In week 11 and 12, will be studying the graph algorithms, BFS and DFS.
Yes, so we can do week 10.
At least week 9 is clear, right? Even I haven't gone through much detail since the deadline has been passed, and assuming everyone
Yeah,
has solved
please go.
something,
Yeah,
I'm
please.
going through it briefly.
Okay, sir. Good.
Okay. Okay, just wait for a second. I'll switch the slides.
Sir, you are mute.
Sorry. So in week 10, we'll be using the matrices to discover the path, reachability, and distance. Okay. So in week 10, we'll be majorly using the train dataset, not marks datasets or something. So using the train dataset, we'll be computing whether this train can reach from this particular station to this station or not. Uh, because there are so many datasets and there in between also there are so many stations. And using the distance, we can compute what is the number of distances, what is the number of time. So such kind of information we'll be doing in week. Okay. So do before going to just remember this is how the train data set looks. It has a distance, station name, arrival, departure day. This is based on the train. For each train number, it has the number of days this train will run. This is the station names it will go. And similarly, if you go via station wise, it has a train number, arrival, departure, and number of days that train will run. Okay. So these are the things it is there here. If you see, this is how we used to represent the trains of T start and train of T end. So trains is basically a dictionary which will be based on this. So each train dictionary will have a number of 1291. This is the key. And this will have start and which will have the station name, and end it will have a station name. Okay. So assuming this is the dictionary structure, so we'll try to see what are the stations each train can have or whether this path can be there or okay. So in first example, we are just checking the whether the direct route is there from that particular station to particular station. Okay. So the pseudocode demonstrates in order to proceed, find whether there is a direct station is there or not between the start and end. Okay. And we are using another dictionary station index and we are creating a graph for it. And the procedure direct route trains, it's accepting the trains dictionary as I have written the above. And we are creating the another dictionary inside the procedure, which is empty dictionary. And iterating through all the keys, which are nothing but a train number. So for all trains, I'm setting stations of start equal to true, end equal to true. So this will be looking like, so far my station dictionary will look like station. Start is nothing but a station name. It could be Delhi, it could be Mumbai, whatever. For each station, so far what are the stations that has been there in start and end, we are setting it to for all the trains in the train dictionary, not only for specific train. It could be Chennai, whatever the start and end stations, just start and end stations. Okay. We are setting it to, and we are computing the n, which is nothing but the length of the station piece. Now, after mm, giving the station keys, so it will find all the unique stations that are there from start and end. So you will have the list of stations which are which the train where the train can be started and ended, unique keys. So after that, using it, you're creating a new matrices and assigning to direct. So this matrix will help you to compute. So in between these stations, whether there is a direct path or not using the train one. Up to this, is it any doubts? Hello.
No, sir.
Okay. Next, what we are doing? Station index. So in station index, we are creating again empty dictionary, and I is equal to 0. Yeah, just keeping the station index as 0. And for S in keys of the stations. Now it will iterate through all the stations that we have kept in our station dictionary. For station index, what it will do? It will keep the indexing numbers. For example, for each station. Oh, I can write it here, I guess. So for station index dictionary, what it will do is, for example, if Delhi station is there for as a first station in my station dictionary, it will keep 1. Sorry, 0. It starts from 0. And Mumbai will be 2. Sorry, 1. Now I is incrementing every time whenever you are iterating through the keys. And Chennai will be, and so far it will be there. And next, what we are doing for each T in keys of the tree. Now we are coming to our main trains dictionary, and we are iterating it again. And we are taking I equal to station index of trains of T of start. So trains of T of start is nothing but what? It is a station name, right? The starting station name in your train dictionary. And similarly, this is your ending station from your train dictionary. And your station dictionary has station index dictionary has only starting and ending stations with the indices, right? Is it clear or am I wrong? Sorry. Is it clear what I'm trying to explain here? I think this part should not be there. I don't know why this is there. All should be initialized as 0. I think the slide has typo. Okay. And if the station index, station start and end is already there in your station index dictionary, then you set it direct of I and j equal to 1. Okay. Is it clear? Hello.
Yes, sir.
So,
Yes, sir.
so here, okay, this is correct. Not I guess this are correct. This is, should be 0, 1, 2 only. This should be 0, 1, 2 only. So, whenever you find a direct station between those two, you are just reinitializing to 1. That's it, right? Direct of ij. And you are modifying direct of ij matrices. See, we just created a matrices direct ij and we haven't touched anywhere using the direct matrices. We are just have been created and we haven't modified anything. So in direct dictionary, what you will be having? So this 0, 1, 2 represent the row and column number. For example, if Delhi and Mumbai has a direct connection, so Delhi is nothing but row number 1, and this is a nothing but column number 1. So here it will be initialized to 1. This represent, so Delhi to Mumbai as a direct matrices. In direct matrices, if you see anywhere 1, that represent there is a uh, direct matrix from that row I, which is that station I. So station I, station J. So that means the station has a direct matrix from station I to J. And also do remember there is something called directed graph and undirected graph. How many of you know what is mean by directed graph and undirected graph? Manshu, okay. Okay. So others, what about others? So no one knows. Okay. Okay, fine. We'll discuss.
Directed graph has specific direction.
Okay. So let's come to the concept of one of. What does mean by one of roots?
Take one stop at a time.
So if I'm able to reach Chennai to Delhi, this is my starting station, this is my ending station I want to reach. So if there is a direct train, fine. But if there is no direct train, I should reach to the intermediate station, which I can call it as Mumbai. So if so first what will I do? I will go from Chennai to Mumbai and Mumbai to Delhi. So I'm reaching to Delhi. Since there is no direct train to Delhi, I'm reaching to the Mumbai. And again from Mumbai, I'm catching the train to Delhi. So one of represent, so you can reach the station, start station to end station which you want to reach, but only through the one intermediate station. One of represent to one intermediate station. Is it clear? What is one of means? Hello.
Yes, sir. It's clear.
Okay. So now we'll be working with the direct matrices which we computed. So direct matrices will be looking like zeros and ones. So it could be 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. It could be something like this. This one represents the direct matrices and each row will be a station name. Station 1, I can say this is a station 2 and this is a station 3 and this is a station 4. And similarly here, this is again nothing but station 1 and I should use different color. This is station 1, station 2, station 3, station 4, station 5. So this one represent there is a direct station from station 1 to 2. Since this is 1, this is 2, this is 3, this is 4. And there is also a direct route between station 1 and 5. Similarly, here if you take the station 2, from station 2 to station 3, there is a direct route. And similarly for station 5. And in station 3, you can reach station 1, station 3. Uh, this should be 0. Okay, sorry. And you can reach station 5 also. In station 5, similarly, this should be 0. We'll take this as 1. In station 4, you can reach station 2 and station. These are all the stations that you can reach, which represent your direct matrices. Okay. Now we need to find, can we reach station 1 to 3, sorry, station 1 to 2 or 1 to 3 through the intermediate station? That is what the one-off matrices gonna do. Okay. So as usual, we are declaring a procedure, taking direct matrices as input, whatever the matrix we computed. Just a minute. I'm getting a call just for a second, okay? Sorry. Okay, sorry. So using this one-off matrices, we'll be computing whether the start and end station can be reached through the intermediate station. So we are creating the one-off matrices, the empty matrices using n by n. Okay. So this is not a square matrix. So I will take a square matrix instead then. So as we are creating n by n, which is nothing but which is a square matrices. And we are iterating through all the rows of direct matrices and columns of the direct matrices, which is nothing but the keys and uh, rows. Sorry, this is the outer key and this will be the inner of the matrices. And one up of ij equal to direct of ij. What we are doing? Why we are initializing one up of ij equal to direct of ij? If there is already a direct path, I don't need to reinitialize to the one by checking the intermediate station, right? If this direct of ij is already 1, for example here, the station 1 and 2 has a direct path. If direct of 1 and 2, if it is already 1, I don't need to check for the intermediate path. If there is an intermediate station between 1 and 2 or that. That's why we are just initializing this 1 of ij as a direct of ij. Whether it can be 0 or 1, that is fine. If it is 0, we need to check the intermediate station through the k. If it is uh, 1, we don't need to check through the intermediate station. Even if you check it, it will be already 1. We won't be reaching the safe block because this intermediate station needs to be true, which won't be true. Okay. Even if it is true, then it is not true, not a problem. It's k in columns. Again, what I'm doing, I'm iterating through the columns of the matrices. So I'm iterating through the station 1, station 2, station 3, station 4, which I'm taking as a k value. If direct of ik equal to 1, direct of kj equal to 1, then I'm saying 1 of ij equal to 1. And how many of you can understand this?
It will find the common station K in which IK is equal to 1 and KG is equal to
This K basically represents the intermediate station. This K represents basically the intermediate station. We are checking to all the station and we're checking through this intermediate station whether I'm able to reach this station J or not. See, it's a start station I and J is your end station. And through K, which is your intermediate station, whether I'm able to reach from start station to intermediate station, and from that intermediate station to end station, I'm able to reach or not. If it is a I'm reachable, then we'll be having 1 in our direct matrices. Then we are reinitializing 1 up of ij equal to 1. This says through one intermediate station, I'm able to reach the end station. Is it clear?
Yeah.
Is it clear, or shall I go with the two up routes, or anyone having any doubts here?
yes, sir.
Okay, let's go to the two hop routes. So two hop routes means what? So we'll be reaching the station A to B by changing two modes station. That means from if I want to reach Chennai to Delhi, I can reach through two intermediate stations, station 1 and station 2. So now I can exchange two stations, two trains in between before reaching my end station. Okay. So this is called two hop. So for two hop routes, what we'll be doing? We'll be taking two matrices as input, which is direct matrices, which will have one value for all the stations, which can be directly reached. For one hop matrices, which we have previously computed, which will have one if the station is reachable through one intermediate station. So you are computing the keys as usual. Since both will be same number of keys, you can take it from one hop also. Since both matrix rows and columns are same. Okay. And two hops, we are creating a new matrices for two hops and n by n. Again, what we are doing, we are iterating through the rows and columns of the direct matrices. And here, if you carefully see what I'm doing is I'm initializing the two op matrices through the one op matrices, not through direct matrices. Earlier we initialized through direct matrices, but here I'm initializing through the one op matrices. Why? Because I already know there is a start to end station between the one intermediate station. So I don't need to check through the two stations. Since I already know through the one-off matrices, I already have a path between these through one intermediate station. I can safely initialize to the one-off dictionary or matrices. And now again, I'm iterating through the columns of the direct matrices again. Now what is it doing is one-off of ik and direct of kj. But why now we are checking with one-off of ik and one-off of kj? So now why we are checking with one op and sorry, this should be direct. K means this I and K and this K and J. Since we already know using the one-off matrices, there is a path through the one intermediate station. Now I need to check, since there is already a one intermediate station through the one-off matrices, I just need to check another intermediate station. So I am using the direct matrices for it. Is one intermediate station is already present using the one-off matrices, that you are sure. But to compute the two intermediate matrices, I just need to compare with direct of Kj. If both are 1, I can safely initialize 2 op of ij equal to 1. So this 2 op of ij again, it will be 1s and 0 where it is 1. So it says from station A to station B, I can reach through two intermediate station. There is a reachability. Any doubts here?
I can't understand one hop and is one hop and two hop on.
Sorry, can you repeat again?
I mean, I can't understand this verse. Why we initialize two hops into one hop?
Why we are initializing 2 ops of ij equal to 1 op of ij?
Yes, yes.
Since we already know there is a direct route through the one op station, there is a in between one station. So I can safely initialize one op of ij, right? Instead of direct of ij. If I'm initializing direct of ij, that is also fine. But the problem with direct of ij is, if this condition is false, 2 of ij, that will be 0. You won't be updating to what? This 2 of ij will say, basically it's taking a copy of 1 of ij. If I take a matrix for 2 ops, for initially, if I'm taking 0, 0, 1, 0 and 0, 1, 0, 0, 1, 1, 0, 0, 1, 0. If I'm taking a 4 by 4 matrices like this I just taken a copy from the one of matrices. Okay, that is what we are doing. This one represent, since this is I have copy of one of matrices, this one represent there is a direct route from A to B station to one of the intermediate station. I don't mind if there is a intermediate station or not through one station. If it is, if I'm able to reach through one intermediate station in the two of matrices, it's well and good, right? I don't need to go and check for the two of. Even if it is a direct route, then also it will be what. So I just taken a copy for to ease my purpose. And why we are taking one of instead of direct is, why the direct matrices doesn't say whether you are having one intermediate station or not. That's why we have taken a copy of one of matrices, since it's already having one intermediate station in between. So we just need to check for one more intermediate station. Are you getting my point? Instead of checking two intermediate station in this if condition, I'm just checking only one intermediate condition. So one intermediate station. That's actually easier to check, right? Instead of checking two intermediate station. Because this one of says I already have one intermediate station. Is it clear?
Yes, sir.
Then finally, it is n hop routes, which I won't be explaining. Okay. Finally, it's n hop routes. What is it doing is, So every time we take direct matrices and n-op routes. So you take one more hop, which is nothing but the n-ops. Okay, this is the n-ops. This is nothing but the n plus 1 ops. And you re-initialize with n-op matrices, which is n-ops. So for example, if you want to find a 5-op matrices, you take a copy of 4-op matrices. Since it will already have the uh, 4 intermediate station, you just need to check with direct and the 4-op matrices. It's similar to that, okay? And you just initialize 2, okay? So then we are checking with the discovery path, which is again the same, I guess. Whether there is a direct edge between procedure or not path extends, okay. And the one op and direct op again we are extending direct matrices and okay, this is same. So using this we can also say whether from this station A can I reach station B or not, and in between there could be n stations. If we are finding n of matrices, so ultimately it tells whether I can reach from station A to B or not. I don't mind whether how many intermediate stations are there. If I catch this station A, whether can I reach station B or not through the intermediate station. So that is what your n of matrices is, right? Is it clear? Basically, it's same code. It's nothing new. So how many of you are still confused? Hello, are you guys there?
Yes, sir.
So is it clear or should I explain once again?
So
So
do we have
clear,
to
sir.
compute n hops before proceeding? Like
Before?
we have to find n hops between the station.
Hmm.
So
So ultimately,
we have to create
uh,
one more graph, one hop, two hop, three hop, and then ultimately we have to find the n hops. Is it like that?
yes. So
Okay, thank you.
the concept here is if you are finding n ops, ultimately you will getting whether there is a path from station A to B or not through the intermediate station. That's what they are trying to teach. Okay. In exams, you there won't be n op matrices and all. Okay, let's go to the next one. So here now we are adding information to the direct route graph. So this pseudocode which we have seen in previous lecture or slide, this is the same pseudocode where I am initializing start and end equal to true. I'm creating station index, I'm iterating it, and I'm creating a direct matrices. But if there is a station A to B and I added an edge, but I want to add some more information through the edge. How can I add? Instead of just saying one denotes there is a edge, right? So,
Yes,
I
sir.
want to add a information like distance. For example, 65 kilometers are there from station A to. how can I add that information? Because distance is a very important information, considering I'm able to reach from station A to B. Or time, I want to add, it will take 70 minutes to reach from station A to B. So these are important informations which I should have in my edge, right? In the matrices also, or you can say. How can I add this information? So we'll look at it. So what we did is we created a one more inner dictionary here, right? You see, we created a one more inner dictionary with direct of ij equal to empty dictionary, and adding a information station B station ends and maps to the row station as usual, and initially an empty dictionary, no direct connection. So this ij represents there is a direct connection, and taking ij and you're taking with t. Now here we are not adding a distance or something. So it says this t, through this station I'm able to reach the station A and B. So the direct matrices will be looking like direct, and for example this station name Delhi will be having a key, and it will reach to the end station called Mumbai, and this T denotes the train number, which is I will be having one more key, and let's say 12291 is the train number, and it will have, and this says through this T station I'm able to reach Delhi to Mumbai. That is the intermediate information I'm adding. Okay, this we can't represent through the matrices, but when we go and compute the distance of it, or the time taking to reach station A and B, that we can represent in a matrix form with direct of ij itself, without having the third in second inner dictionary. Is it clear what we are doing it here? Hello.
Yes, sir.
So let's go on next one. As I said, now what we are doing is we are storing the distance through the edge. So generally how we used to initialize? We used to initialize direct of ij equal to 1 if there is a direct station between station I and j. But here, instead of initializing to 1, what I am doing is trains of t of distance, right? So this, instead of initializing to 1, I'm initializing as a distance, for example 70 kilometers. So there will be a node something like this, A, B, and I'll be drawing an edge. This earlier this edge represents 1. 1 means there is a reachability. That's it. Now my edge will have a information of 70. This 70 represents I can reach station A and B in 70 minutes. So that is what I'm storing now. And if I'm able to find a direct distance through any other train, sorry, yeah, through other train from station A and B. So instead of 70, for example, through 70 minutes, I'm able to reach to the train number 12290. But through the 12291 train, I'm able to reach the same start and ending station by 60 minutes. So my now edge will be 60 minutes, not 70 minutes. So that is what this else block is doing, minimum of the distance which it already has and the new distance which you have seen. So it's taking minimum of that and adding it here. So now how my matrix will look like in this case? Earlier we have seen a matrix with just zeros and ones, right? Now my matrix will look like, for example, represent A, B, C, D as a station names and A, B, C, D as a station names. So instead of, I'll put zeros diagonally. It denotes I cannot reach from station A to station A itself. That means it doesn't have any circular path. Okay. So from station A to B, I can represent 60, I can represent 30, and 0. 0 means I won't be able to reach from station A to D. But B and C says I can reach from station A to B by 60 and station A to C by 30. The 60 and 30 denotes minutes. So I can reach from station A to B by 60 minutes. From station A to C, I can reach by 30 minutes. Similarly, I can reach from station B to A in 25 minutes, which is not supposed to be in real case, but it might, if you are considering pseudocode, it might have, right? Because there might be another station which runs from B to A and which could reach in 25 minutes, but there could be another train which runs from A to B, which takes longer time than as usual. If it's having more intermediate stops, it will have more number of time. It will take more number of time, right? So similarly, it will have the values instead of zeros and ones. So this is what my direct dist matrix will be look like instead of having zeros and ones. And this we call as a edge labeled graph. So if I want to denote as a node, this is my edge and edge is having some value and that is called edge label graph, or you can say the weighted graph. In terms of in normal matrix, normal term, if I wanted to say, I can say as a weighted graph. Okay. Any doubts here so far? If there are no doubts, okay, we can
None.
move on. If any doubt, we can discuss. In week 9 and 10, it's very important. All the matrices that we'll be seeing will be weighted graph, and you will be studying directed and undirected graphs also. Sorry, 11 and 12. Okay. Then we'll move to next one. I'll just erase this. So here what we are doing is through the one-off distance. Now we are computing the distance matrices through the one-off distance. You can see it's same code. I'm just taking one-off matrix, one-off distance matrices instead of one-off. I'm creating matrices again. I'm iterating to the direct list. So direct distance will have, instead of zeros and ones, it will have the numbers. And in order to initialize one-off distance matrices, I'm just taking a copy of direct distance matrices. And for k in columns, again, I'm iterating through the columns, which is nothing but a station. If both of my values are greater than 0, it's checking that through the intermediate station, I'm able to reach it or not, right? Earlier, we checked whether it is equal to 1 or not. Since now we won't be having 1 because this the weighted graph will be having some numbers, we are just checking whether it is greater than 0 or not. So this stays start station and end station, sorry, intermediate station, again intermediate station to end station. So if both are greater than 0, that means there is an intermediate station where I can reach from start station to end station. So through this, I'll be able to reach my final station to the through the one of the station. So my new distance will be? My new distance will be direct of dist ik and direct of dist kj. Okay, this is my new distance will be through the intermediate station. Again, you have to check whether the one op is greater than 0 or not. That means there is a uh, not a path. There is already some distances already exist. That means what you are doing, you are taking the minimum value. If there is already path, you are taking the minimum value of I comma j. Sorry, minimum of the new distance and the existing value. Else you are initializing the new distance, whatever you are computing. Is it clear? Or any doubts here on our distance? Any doubts? Hello.
Yes, sir.
Okay. Then I think that's all in week 10. So in week 10, what we saw is, I'll just briefly summarize what we have saw. So in week 9, we saw uh, how to create matrices. It is the major thing which we have studied. And in week 10, we saw the station reachability to the matrices, whether can we reach from one station to another station, and station one op, two op, and up to n ops they just computed through the intermediate station, whether can we reach or not. And same thing we did using the time also. Instead of having direct of ij just zeros and ones, so we just computed the time and replaced with one values, right? Station reachability through the, what is the time it would used to take from station A to B through the one op, two op from the direct stations. This is what we have studied in week 9 and 10. But in week 11 and 12, you will be studying BFS, DFS, all these things will be there. And similarly, the adjacency matrix will also be there. Adjacency matrix. The adjacency matrix is nothing but whatever the matrix we are created with zeros and ones, or the station A to B, there are some distance, that is called adjacency matrix. Okay. And there is something called adjacency list. which we'll be seeing in week 11 and okay. There are other algorithms also. I don't know whether the topological sorting has been covered or not. That will also be there in week 11 and 12. So be clear with matrices, whatever you are studying right now. So in Monday session, there will be a solving of PA questions. So be clear with it, whatever you are trying to solve. Otherwise, it's very difficult to get the concepts of week 11 and 12. Okay. And also try to see if I compute a matrix, something like 0, 1, 0, 1, 1, 0, 1, 0, how can I visualize as a graphs? That is also important. I don't know whether it has been started in Max 1 or not. The Max 1 also covers the same concept.
It started this week, graphs in Max
Okay.
10.
Okay. Then. Okay. Any more doubts? Whatever we have studied so far. Okay. Then if you guys are having no doubts, then we can wind up the session. Okay. Uh, okay, guys. Then thank you for joining. Bye bye. Have a great day.
Hello. Hello. Hello.